Yesterday we made the transition from relatively simple two-dimensional collisions where maybe we have one car going east and one car going north colliding at an intersection, and from an explosion where we have maybe three pieces go off after the explosion, one to the north, one to the west. Where does the third piece go? To problems yesterday where we had funny angles like 18 degrees or 27 degrees or 13 degrees. When we have collisions involving those funny angles, it becomes a little bit more work and a little bit harder because we've got to deal with that funny angle that we didn't have to deal with before. When we have a situation where maybe an object is going this way at 25 degrees, and maybe an object is going this way at 17 degrees, and then they collide, and then they head off, maybe as one object, maybe as two objects, it doesn't really matter. Let's say one object after the collision. We've got to deal with those two angles, that 25 and the 17, in a way that we didn't have to deal with them before. Okay, when it's like this and like this, we don't have to deal with the angles. We have just X and Y. We don't have some kind of combination of X and Y at the same time. So how do we deal with these? Well, what we do is essentially take that 25-degree angle, draw a little diagram off to the side. Okay, we've got a 25-degree angle right here. This is an X component, this is a Y component. Let's find the value of the X component of that. Let's find the value of the Y component using some trigonometry. And then let's erase this and let's replace it with this. We can deal with that. Hey, that's easy because that's straight up and straight across. We know how to deal with that. Similarly for the other diagram, we've got a 17-degree angle. Well, let's draw a little picture over here and resolve that. 17 degrees, this is X, this is Y. Find the value of X and Y using some trigonometry, and then erase that and replace it with this and this. Again, now we've got a more straightforward problem where we don't have those funny angles. It's just straight up and straight across. All right, let's do those two problems that we had for homework last night on page 491. Both good questions, both a little bit different actually. There's bits of both of them that I think are useful to go through here. The first one says a 97-kilogram hockey center stops momentarily in front of the net. He's checked from the side by a 104-kilogram defenseman traveling to the east. So let's draw our hockey center, our light guy, not our light guy, he's 97 kilograms, our lighter guy. He's still about 220 pounds. We'll call him object number one. He's stopped in front of the net, so his velocity is 0 meters per second, and of course his mass is 97.0 kilograms. Object number two, we're going to draw in green. He's going to the east. His mass is 104 kilograms, and his velocity to the east is 1.82 meters per second. Now, the wording of this, I found the wording of this to be a little bit tricky, actually. I don't know about you guys, but it says he's checked from behind and bounces off at 0.940 meters per second. Which guy bounces off at 0.940? Is it the green guy or the blue guy? The heavy guy or the light guy? Which guy is it that bounces off? The heavy guy? Okay. He's checked from the side by a 104-kilogram defenseman skating at 1.82 and bounces off at 0.940. The 97-kilogram hockey center is checked from the side and bounces off at 18.5 degrees south of east. It's the lighter guy, isn't it? Okay. The guy that's at rest is checked from the side and bounces off at that angle and at that speed. So we're going to say that guy number one is going down here at 0.940 meters per second at an angle of 18.5 degrees. Now, where do you think guy number two is going to go? The heavier guy, the defenseman that's checking him here, Andy? Yeah. What do I have here? Oh, yeah. Yeah, I've got this drawn the wrong way then, right? Yeah, you're right. Absolutely right. So we got guy number two going this way, right? At 0.940 meters per second. Holy cow. Must have been the fire this morning that messing with my mind here. 1.82 meters per second, and 104 kilograms. Okay, thank you, Andy. So guy number one is going south of east. So guy number one is going to go down this way at 18.5 degrees. If I make him another mistake, Andy, just point it out. Just jump up and yell at me, okay? He's going at, I better not make a mistake now, 0.940 meters per second. Where's guy number two go? The heavier guy, Kenton? Yeah, he's going to go north of east somewhere. Exactly where, we don't know. We got to figure that out, right? But we know he's going to go up there somewhere. Well, listen, it's got to be north and east, right? If we have a momentum, a vertical momentum of 0 before the collision takes place, then we have to have a vertical momentum of 0 after it takes place. If one's going down afterwards, then one's got to go up afterwards in order to cancel that out. So up and to the right. All right. First thing that we see when we look at this question is that angle, the 18.5 degrees. It jumps out at us. We don't like funny angles, so we got to get rid of it. So let's, off to the side somewhere, let's figure out the x and the y components of that 0.940 meters per second. Let's just do it right here. Okay, the hypotenuse is 0.940. This is x, this is y, and we got an 18.5 degree angle here. Listen, if we got to find the x component, we got to know whether it's the adjacent, opposite, or hypotenuse. Which is it? Which is it? Kate, which is it? Opposite, adjacent, or hypotenuse, the x component there? Good. So if it's the adjacent side and we've got the hypotenuse, which trig function are we going to use to find that value? Good. Cosine 18.5 degrees is equal to adjacent over the hypotenuse. Kate's side of the room is going to solve for that value, okay? Now the other side of the room is going to find the opposite side, which is the y component. Sine 18.5 degrees is equal to y over 0.940. Parker, you get the answer? Okay, what is it? 0.8914, thank you. And this side of the room, you get the y component. 0.298, thank you. All right, so now I got this little aside over here. I've resolved that 0.940 meters per second into an x and a y component. What I want to do at this point is redraw it. Like, scratch this out, erase it. Or if you can't do that because you've got it drawn in pen, just redraw it. We have 0.8914 to the right, and we have 0.298 downward. Now we don't have a funny angle. We do up at the top, actually, for object number 2, right? That's a funny angle. But we don't know what its value is, and we can't do anything with it right now, so we're not going to lose any sleep over that one. The one that we could do something with, we dealt with it, we did something with it, and now we've got no funny angle there to deal with anymore. Now let's solve the problem. Okay, we've got x and y components. That's what we do when we have a two-dimensional collision. Okay, we still have to do x and y components even though we've dealt with a funny angle. Basically where we're at right now is a problem like we had 2 days ago. We still have to do x and y components. We did 2 days ago, we still do. But now at least we don't have to deal with this funny angle of 18 degrees or whatever it was. Let's say pi is equal to pf. Let's say m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. All right. Something I can x out here. Can you tell me what it is that I can x out? What it is I can scratch out? Yep. Good. Why? Why can I scratch that one out? Good. Okay, this hockey player, the centerman, 97 kilogram centerman, is standing at rest in front of the net here. So his momentum is 0. M2 is 104 kilograms. V2I is 1.82 meters per second. M1 is 97. Here's the big test. What's V1F? Garrett, what's V1F? No. Guys, everybody look at the question, okay? I don't care if it takes a few seconds to come up with an answer. I'm okay with that. I'll wait. I'm patient sometimes. Right now I am. Everybody look at it and see if you can come up with the answer there for V1F. Okay, work through it. V1, object number 1, final. Okay, so the velocity of object number 1 after the collision, x component. John, you got it there? Good, 0.8914. Right, does that make sense? Plus M2 times V2F. We don't know what V2F is, do we? We don't know what its x component is. So get this number, take this over by subtracting, and then divide it by 104, and we should get the value of V2F. Someone's got to have that for me. 0.989. Anybody agree with that? Okay, thank you. All right, good. X component's done. If this is a multiple choice question, what do you think the odds of that being one of your options are? Probably pretty good, right? Right, we work through these questions, and then we get so mad, so frustrated when a multiple choice question gives us an answer that, oh, hey, we got that. So we circle it, we pencil it in, and we get so mad when we discover it's wrong. Don't look at the answers. That's the key here. Don't look at the answers until you know you're done the question. Then look at your answers. Don't get fooled by seeing an answer that you get that's an interim answer, that's a partway through answer. Okay, let's do the y component now. Again, pi equals pf. A bit of a shortcut here. What's the y component of object number 1? Tara, what's the y component of object number 1? Good. Devin, what's the y component of object number 2 before the collision takes place? Yes. It's moving. Object number 2 is moving, but on the x-axis, right? So the y component is 0. Let's just write in 0 instead of m1 v1i plus m2 v2i. The whole thing is 0. So just pencil it in as 0. m1 v1f plus m2 v2f. Garrett, what's v1f y component? Good, 0.298. But, yes, good, negative 0.298. What's 104 kilograms times V2F y component? Who's got a value for that one? What is it? 0.2779 meters per second. Everybody try that. Make sure you can get those values, okay? All right. Now it's just like all those other problems, right? We've got 0.989 this way. We've got 0.2779 this way, and the resultant speed is this way. Okay, we can find v by the Pythagorean theorem, and we can find theta by taking the inverse tan of opposite over adjacent. Okay, the answer's there. 1.03 meters per second at 15 degrees north of east. Try it. Make sure you can get it. If you don't get that answer, then raise your hand so that we can go over it for you, okay? Otherwise, I'm going to trust that you've gotten it. Let's take a look at question number 2 here now. It says a 1,200 kilogram car attempting to run a red light strikes a stationary, heavier car waiting to make a turn. So we're going to say car number 2, the blue one here, is 1,350 kilograms, and it's at rest, waiting to make the turn. Car number 1 is, we don't know which way car number 1 is going, do we? Okay, what happens here? The 1350 kilogram car, that's the heavier car, goes east of north. So we're going to say car number 2 goes this way, 55.2 degrees east of north at a speed of 8.30 meters per second. And then it says car number 1, the other one, the lighter car, goes the other way. We're going to make that one green. This one's 36.8 degrees west of north, and its speed is 12.8 meters per second. All right, we don't know which way car number 1 is coming from, the 1,200 kilogram car. Anybody want to take a stab at it, a guess at it? Yeah. Coming from behind here. Now, is it coming straight from behind? Is it going straight north before the collision? Well, we don't really know, do we? It looks like maybe it should be, but we don't know that for sure because we're not told that it's going straight north before the collision. We can't assume that. Okay? If listen carefully, if we were told that it was going straight north before the collision, then what component would you likely want to do first? Probably want to go straight to the Y component, right? If it was going straight north. Think about that. If we know it's going straight north, if we're told it's going straight north, why would we bother trying to solve for the x component of its velocity when we know it's going straight north? Because the x component would be 0. Now, we don't know that it's going straight north, so we do have to do x and y components. The bad news is I got 2 funny angles here, so I got to get rid of them both. Let's draw a little aside again. Here's the 8.30, x, y, 55.2 degrees. Which trig function do I use to find x? Shaylin, which side of the triangle is it? Right, if it's opposite, I'm going to use which trig function? Good. So let's say on this side of the room, use sine function to find the x component there. The y component, therefore, Shaylin, is going to be the cosine function, right? Because it's the adjacent side. This side of the room, let's use the cosine function to find the y component. 6.82 for the x component. Agree with that, guys? Thank you. For the y component over here, 4.737. All right. There's one of them. Now let's do the other one, okay? Because got 2 funny angles here. The other one is 36.8 degrees this way. And the speed was 12.8 meters per second. The x component is, once again, the opposite side of the triangle, so it's going to be sine. The y component is the adjacent side, so it's going to be cosine. Andy, do you have the value of the x component there? $6.82? No, that's the other one, actually, yeah. That's okay. Anybody else? Parker? 7.67 meters per second. And the y component, somebody? 10.249, thank you. There's my other little aside. Now, what I like to do at this point is erase this and replace it. We don't have to do that, but for some people that's helpful. We've got a 6.82, and we've got a 4.737. Now for the other one, I can erase that one as well. Get rid of that funny angle. We've got a 7.67 to the left. And we've got a 10.249 upwards. Now let's deal with this question the same way as we've dealt with the questions 2 days ago. X and Y components. Remember, if we knew that it was going straight north before the collision, we wouldn't have to deal with the X component because you'd solve for V initial X component. It's of course going to be 0, but we're not told that, so we've got to deal with the X components here. We're going to say PI equals PF, M1 V1I plus M2 V2I equals M1 V1F plus M2 V2F. We can cross out one of these. Cross out one of these, right? Which one is it? Javi, which one can I cross out there? Which term? Yeah. Object number 2 is at rest, so its momentum is 0. Object number 1 is 1,200 kilograms. We don't know what V1I is. Let's solve for that. Ken, what's V1F there? V1F. V1, remember, is the green guy. V1F X component. Yeah, we'll make it negative 7.67 because it's to the left. And V2F X component. V2F X component. What do you get for that one, Vlad? Good, and it's going to be positive, right? Because it's to the right. Solve for V1I there, X component. I think it works out to be something times 10 to the minus 5 or something like that. Like a really small number, right? Andy, what is it exactly? 2.3? Andy, what'd you get there again? Now, this one is highly dependent upon the number of decimal places you use. So you could get a slightly different number than that. In fact, a fairly significantly different number than that and still be correct depending upon how many decimal places you use. The good news is it's not going to matter. In a moment, you'll see why. Let's do the Y component here. PI equals PF, M1 V1I plus M2 V2I. Um, 1,200 times V1I. We can still cross this one out because it's at rest. Okay, let's look at this. V1 F Y component. Mark, what'd you get for that one? V1F, object number 1, the green guy, final, Y component. Good, 10.249, good. Lots of numbers here, right? It's a little bit confusing. 10.249 plus 1350. Kyle, V2F, object number 2, the blue guy, final Y component. Good, 4.737. And they're both positive because they're both upwards. Who's got a value for that? Andy, you get that one too? 15.9 meters per second. All right. Take a step back from this for a second, guys. Look at what we got for the X component. Look at what we got for the Y component. How do you put those together? Well, draw a triangle, do the Pythagorean theorem. But when you do that, what are you going to get? When you combine 10 to the minus 5 with 15.9 using the Pythagorean theorem, you're going to get 15.9, right? You do the inverse tan function of opposite over adjacent, what are you going to get? 0. Is it 0.6? 15.6? It's the kindergarten influence, isn't it, Andy? Mix up the 6s and the 9s. Yeah. That's what happens when we get kindergartners in the school. When you combine these guys, you're going to get 15.6. Okay, the angle you're going to get is 0 degrees. So essentially, what do we know? It's going straight up, right? Somebody guessed that it was going to the north before we started this question. You were right. We didn't know that for sure, so we couldn't assume it, but it turned out you were right. It's kind of like that problem yesterday. Remember when we had the coal falling, right? The mass of the Earth had to be taken into account for the y component, and if you did account for the mass of the Earth, then the final velocity y component was so ridiculously small that it didn't matter. Well, here we go. The x component is so small here that it doesn't matter. Kind of like the same thing, right? I'd like everybody to take a look at multiple choice number 19 right now, and you're going to submit that one after you've completed it as multiple choice number 1. Remember, your options are A, B, C, D, or E if you don't know what you're doing. Don't guess on this. Okay, submit option E if you're not sure what you're doing. All right, guys. Look at this question. Clearly a two-dimensional collision. Clearly it's going to be a conservation of momentum problem, an x and y component problem. Clearly we got a funny angle. No, wait. We got two funny angles here. We got 67 degrees and we got 23 degrees. Here's the thing, though. And I know I had this question from one person. Probably more than one person had it, just didn't ask it. The second angle there, the 23 degrees, we can't really do anything with that right now. We can't get rid of a funny angle when we don't know anything else about that vector. So the only one that we can deal with is the 67 degrees, 0.14 meters per second. So let's do that. Let's go off to the side over here. 0.14 meters per second at an angle of 67 degrees. Let's get the x and the y components for that. Now, x is which side of the triangle? Adjacent side. So which trig function are we going to use? Good. X is going to be the cosine function. Cosine 67 degrees is equal to adjacent over 0.14. Who's got a value for that x component there? 0.0547 meters per second. Thank you. Now let's do the same thing almost for the y component. Sine 67 degrees is equal to y component over 0.14. Y is equal to 0.14 sine 67. And what do we get, Josh? What do we get for that one? For the y component there? Yeah. 12887. Okay, thank you. Now, what we can do here at this point, if we want to, is replace this with this, 0.0547. And we could replace it with this, 0.12887. Now, the other one, again, we can't do anything with at 23 degrees. Okay, we're stuck with it. The good news is we don't have to. If you can't deal with it, if you can't get rid of the funny angle, the good news is you don't have to get rid of the funny angle. So whenever you need to get rid of it, you can do it. All right, let's do our x and y components here. See if we can find some space to do that. Let's say for the x component, pi equals pf. Let's say m1, v1. We'll call this object number 1. We'll call the blue object number 2. m1, v1i plus m2, v2i equals, they don't stick together, m1, v1f plus m2, v2f. Good news. Shortcut here. What is it? Okay, so we can cancel out all the masses. What else are we saying, Parker? Good. V2i is 0, so we can scratch that out. The initial momentum of that one is 0. That leaves us a V1i, 0.36, equals V1f. V1f. We don't know what that is, do we? We got an angle there, 23 degrees, but we don't know what to do with that angle yet, so let's just do it the way we've been doing it. Okay, deal with it the way we've been dealing with it, and see what happens here. V1f is something. V2f, x component. Gary, what's V2f x component there? Good. 0.0545. Now we take that over to the other side by subtracting. We end up getting V1f is what? 0.36 minus 0.05, 0.3155. Is that right? Okay, there's my x component. Now what? Well, there's a shortcut at this point. There's a shortcut at this point. You don't need to see it. You don't need to spot the shortcut. But if you do, it saves you some work. Let's do it the regular way, and then we'll go back and do it the shortcut way. Okay, the regular way is to say, hey, look, let's do the y component. Same way as we always do. Pi equals Pf. The initial momentum y component is 0 because object number 1 is moving but on the x-axis. Object number 2 is at rest. So the initial momentum y component would be 0. m1 v1f plus m2 v2f. Masses still cancel. v1f y component is 0.12887. Object number 1 y component. No, that's object number 2, isn't it? Is that 0.3055, yes, up here? Yes? Okay, so 0.3055. V1F y component plus the y component of object 2, which is 0.12887. V1F equals negative 0.12887. Now we can combine these, same way as we always do, right? We got 0.3055. We got 0.12887. We can combine them using the Pythagorean theorem and finding the, hey, we don't need to find the angle, we already have the angle, right? But if you did the inverse tan function of opposite over adjacent, you'd get 23 degrees, the angle that was given to us there. That make sense? All right, what's the shortcut? What's the shortcut? Remember, to find V, it's hey, we do the math there, we get our value for V. But there's a shortcut here that can cut quite a bit of time off this. And you don't have to spot it, but if you do, again, it saves you a couple minutes. Yeah, Josh? Say it again?
So when you take the y value, that's that triangle.
Just,
You cancel out of the masses.
yeah.
The pi minus the pf.
Yeah.
The pi, the y is 0 minus y.
Yeah. Yeah. So V1F is negative 0.12 there. Yeah. Yes. Yes. That's the shortcut right there. You can, if you spot this, skip doing one of the components. Now, it makes sense. Josh said, let's skip the x component because there's more work to the x component, right? Y component's easier. So watch what Josh did. He didn't do x. He didn't do any of this stuff. He didn't even calculate, probably didn't even calculate the x component here. Didn't need it. Why? Because that second vector that was at 23 degrees, he calculated the y component of that to be 0.12887. He already knew the angle was 23 degrees. He wanted to find this speed right here. All he did is say sine 23 degrees is equal to opposite over hypotenuse. That make sense? Listen, a lot of times when you see a question that's a two-dimensional collision on a multiple choice question on an exam, they'll give you a shortcut because it takes so much time otherwise. They'll give you a shortcut. But don't spend 5 minutes looking for a shortcut that's going to save you 2. If you don't spot the shortcut, just do it the long way. It's not the end of the world. It just takes you a little bit more time, that's all. You guys comfortable with it? The only thing we want you to do today, guys, is worksheet number 4. There's 8 questions on that. Let's see how much we can get done in class. And then what you don't get done in class, let's do it for homework tonight.